My name is Dr. Terry Smith. I'm a senior principal scientist here at Dynamic Research in Torrance, California. I manage the Impact Test Lab, which is the laboratory where we do helmet impacts. We look at issues of human safety and product design and development to try and improve safety for individuals in various different activities like sports, the military, automobiles, all sorts of impact events. We do develop our own crash test dummy. We've developed a special crash test dummy called a motorcycle anthropometric test dummy, or an MATD. It's a unique test dummy in that it's designed specifically for motorcycle crashes. We're the only company in the world that actually makes these dummies, and we make them and sell them all around the world to different manufacturers and motorcycle manufacturers and helmet makers and safety product manufacturers. We look at ATVs, we look at automobiles, we look at motorcycles. We do what is called applied vehicle safety. In our lab, we test bicycle helmets, we test equestrian helmets, we test military helmets, we test hockey helmets, football helmets, in addition to motorcycle helmets, and we test, obviously, helmets from all around the world. We are an ISO accredited test laboratory, which means we have been recognized for our quality programs, and we have a quality management system so that we produce reliable, repeatable impact test results. In a motocross off-road crash, the probability of you going off the bike at a fairly low speed is quite high. So you're going to fall to the ground from probably 4 or 5 feet. And when you're doing that, your impact velocity into the ground is probably only going to be about 10 or 12 miles per hour into either a dirt surface, maybe some rocks, some sort of damp surface. So the helmet has to effectively protect you at that type of an energy level. And that energy level is critical because if you look and think about all the different types of crashes you can get into in a motocross accident, by far, those are the type of crashes you're going to get involved in. You know, yes, several riders will go into a tree at a very high velocity or fall from a high height, but the vast majority of riders are going to fall off their bike at a low speed and going to impact the ground. So they need a product that's going to provide them protection down at these low energy levels. When your head falls and hits the ground, you have two types of motion. You have linear motion, meaning translating in a straight line, and you have angular motion, which means you're rotating about a center mass, a point of rotation. So if you think about how your head is made, it sits on your shoulders, supported by your neck, and so when your head rotates forward, it's going to translate, meaning it's going to move in a straight line, but it's also going to rotate about your neck, because obviously we're still attached to our bodies and our head rotates. So when we rotate, we induce both this linear motion or linear acceleration and this angular motion or angular acceleration. So both of them are very important in trying to protect against head impacts. Well, when a dirt bike rider goes over the front of his handlebars, he's going to come down forward. His chest may land on the handlebars, so his head is going to start to rotate forward. He's going to fall forward off the front of the bike down into the ground. So we've got both rotation as he's coming down to the ground, and we're going to have a linear impact vector because he strikes the ground. Both of those are very important, and we want to try and manage those in an efficient manner to try and provide the most protection we can. When a motocross rider goes down, we will hit the ground in 3 dimensions. We don't travel linearly in one straight direction. We travel along 3 different axes or in 3 dimensions. So in order to understand the total acceleration, we have to compute what's called a resultant, which is really simply the summation of the 3 different directions. And we can sum both the linear acceleration to form what's called a resultant linear acceleration, and we can also sum the 3 angular acceleration components to form what's called a resultant angular acceleration. Both of those are really important because that expresses the total magnitude of the forces that are being applied to your head in a given impact. All the standards that are out there in the world, internationally, DOT, Snell, the British standard, the ECE 22 standard, all of these standards measure only linear accelerations. So therefore, we're only getting part of the picture. We're only getting the linear acceleration measurements. The testing that we've done today is unique because we measure both the linear acceleration as well as the angular acceleration. And as we know from our epidemiology data, concussion is strongly linked to angular acceleration as well as linear acceleration. So we need to measure both. Most traditional tests are what are called drop tests, in that we have a monorail tower that basically controls the motion of the head form, or that you use to simulate a human head. It can travel in one direction. It usually drops vertically onto a plate or some other type of anvil. So that makes the measurement quite simple, because you can put what's called a uniaxial accelerometer or a single axis accelerometer. So you measure that acceleration in one direction. Now, as I said earlier, the human doesn't travel just in one direction. We need to understand three-dimensional motion. So our testing is different, because what we've done now is using an incline anvil. We are trying to induce the rotation in our helmet and in our head form. And by doing that, what we're going to do is we're going to be able to measure both the linear and angular acceleration for a given impact. In terms of international standards, there is no standard out there that actually includes angular acceleration. So we are working within ASTM, the American Society for Testing and Materials, to try and develop new forms of head protection standards, including an off-road standard that potentially could include angular acceleration measurements. So it's a new and innovative area that could hopefully advance helmet standards and start looking at angular acceleration measurements. DOT and the Snell are very similar because they're both use a monorail drop tower. The DOT involves drops from 72 inches or 6 feet onto a flat anvil, 48-inch drops onto a hemispherical anvil. Snell uses both flat anvils and hemispherical anvils, but they have a much higher drop height. They deal with, they ask the helmet to manage a lot more energy. CE standard is different because it uses what's called a free motion head form, meaning it has a triaxial accelerometer, and the head form is allowed to rotate because it's suspended in a basket. All three standards work really well in that they provide excellent forms of head protection. Snell has their, they have their products, they have their standard, and they've, been developing and promulgating the standards for a long period of time. So they have their areas of interest. I think right now there's an incredible public awareness of concussion, an incredible awareness of the risks of concussive injuries and the long-term problems associated with it. So therefore, a lot of focus on standards and head protection is now migrating towards concussions. We used to be worried about skull fractures and subdural hematomas and other more significant brain injuries. But now, because a large percentage of the population are sustaining concussions, you're seeing a lot of new research and new efforts to try and understand concussion. Motocross is not unique. I mean, equestrian has problems with concussion. Football and all contact sports obviously have problems with concussion. So it's a large area of research. There's a tremendous amount of research being done. So hopefully all of this information will help us make better helmets and better forms of head protection. There's a large growing population of people that go out and do BMX, downhill mountain biking, motocross, equestrian activities, obviously football and hockey. All of these areas have a high concussion risk, and there's lots of concussions being reported. So the mechanisms across all of these different sports and activities is all the same, because we know biomechanically that the mechanism is the same. So therefore, we have lots of opportunity to develop standards and understand how technologies can work to try and reduce both the linear and angular accelerations to provide better head protection within the same package. So. From our height, it's probably about 10 miles per hour in the low drop height. And when you get up into the higher drop heights, which is near 2 meters, you're probably looking at about 15 or 17 miles per hour impacting into the ground. An important factor is we're talking about the vertical impact vector. We're not talking about how fast you're riding forward. We're talking about how fast you're going down towards the earth. That's a very important fact to remember. And what we're doing is, in most drops, it's that vertical vector impact into the ground that causes the most damage in terms of head injury. It can be the ground, a curb, a rock, any type of thing. But once again, it's the vertical vector down into the ground. Forward vector will add to rotation of your body as long as you don't run into a vertical object like a tree or a rock or a post. And most riders don't on motocross. They tend to hit the ground and rotate out as best they can. So it's this vertical impact velocity that we want to pay attention to. We know traditionally from epidemiology, we know that in order to provide protection against concussion, we're going to have to reduce the linear acceleration, and we're also going to have to reduce the angular acceleration. Linear acceleration can be managed quite effectively by the expanded polystyrene or the liners. And the angular acceleration is a much greater challenge, because what you have to be able to do is you have to figure out how you can slow the head down from actually rotating. And the technology that they've developed actually takes, using their technology, they try and slow down that angular acceleration of the head. So it looks like a very promising technology. It's great because we know the nature of the problem, but we need creative solutions to try and address that. And that's exactly what 6D does, is it's a technology that basically tries to absorb that angular acceleration. And hopefully we're going to get out there and see that it's going to work with riders. One of the things that we also are doing with the 6D helmets is we're taking the data from our tests, the linear and angular acceleration data, and we're feeding that information into a finite element model to try and understand at the tissue level what the brain is doing under these type of rotation situations. And we're just starting to look at that research and gain better insight into how this product performs under those type of impact situations. What I really like about my job is that I get to see new and innovative technologies. I get to be out on the leading edge of technologies that can potentially make a difference. And I get to evaluate products and promote helmet safety and head protection in many different venues, bicycling, motorcycling, all around the world. Any technology that can have an immediate impact is a great technology, because you want to get out there, you want to develop a product that the end user finds acceptable, that they like, that they're willing to wear and put on their head. I can develop the safest helmet in the world, but nobody's going to wear it. So you have to find that balance between developing a good product that the riders will like and wear, and a product that provides new and innovative technology.